All right, hi everybody, welcome back to our C++ programming course. So what are we going to talk about today? Today we will talk about mainly error handling. So, and all the different kinds of error handling that you might wish to use within your code, within your programs, namely the three categories exist which are listed here. So we can use return codes for error handling. We can also use assertions or exceptions. And then on the very last few slides, we will also see some some different kinds of pointers. So far we only have been concerned really with pointers to values, to variables, but you can also have some different kinds of pointers, mainly pointers to functions, so function pointers. And there's also a special type which is defined in the STL, stud function, which allows you for an easier, a safer usage and handling of function pointers. So let's start and let's talk about error handling. So how to handle program errors, that's basically the topic of today's lecture here. And of course, unfortunately, I cannot give you a concrete answer because, how to handle program errors highly depends on your problem that you're going to solve using the C++ programming language. So it depends on your domain, on the specific functionality that you implement. So I can't really give you an answer, and that's quite sad. But what's more important, what I can give you, what I can tell you how to detect errors, how to recognize them, and how to handle them is then your task, and it's your problem that you need to solve depending on your context. So I already showed you on the first slide, really, list all the topics, the three important mechanisms. So, we have four mechanisms of handling errors, and the fourth one shouldn't be used at all, I guess, because the fourth mechanism is just ignore errors. And nothing bad will happen. I can just implement my code in that way, and it will probably work. And I can really tell you from experience, it won't work if a pointer can be null that you may receive as a function argument. At some point it will also be null, and then you run into huge trouble. So please do not think, this is a very rare circumstance. It won't happen probably. Yes, it will definitely happen. And the one case you forgot to cover is the case that will lead to a program crash. So please do not ignore errors under all circumstances. So that's just not acceptable, really. But I hope that that is clear anyways. Also, you can use return codes as a proper way of handling errors and communicating errors in your program. You can use assertions. People learn that there are static and dynamic assertions, which you can use to ensure your program's correctness while implementing it. And finally, at last, we will talk about exceptions, which are the ultimate way of handling errors, so to say. And we will also discuss pros and cons. So it's not always advisable to use exceptions, but many times exceptions are great. They're doing a great job of handling errors. And again, handling errors is really an important part of computer programming. So you have to know all the mechanisms, all the different things you can use in order to really write good programs and good pieces of software. We already run into an issue really when we had to implement the scalar product function. If you remember, the scalar product function took two vector arguments and it computed the scalar product of those two vectors. So basically, a scalar product is the angle between two vectors. That's what a scalar product is according to mathematics. And we had a huge problem, and the problem was, what should we do when those vectors have different lengths? So the scalar product is only defined really for vectors that have the same length. And I mean, in your program, it could also be that you receive two vectors as arguments with different length, and then yeah, you are in trouble. You need to deal and cope with that situation somehow. So here is basically the problem once again. And if you now imagine maybe for one moment that you're maybe a math library implementer who also charges a lot of money for his or her library, then yeah, your customers basically who pay you very much money wish that your code, the code that you write, the library code should work reliably, of course. And they also wish to know when something goes wrong by means of good error handling, of course. So you need to do something about that. And yeah, rather than just continuing with the computation and producing nonsense results, so that can't be the case. So again, you cannot just ignore errors really. So why could that even happen? That you introduce an error really in your program? Or I mean, it could be that the user of your function that you implemented the scalar product, namely that the user of that function has no clue about mathematics. Maybe he is not aware that the vectors have to have the same lengths. Yeah, it could be the case. Maybe the user has made a typo, and instead of passing the vector variable a, he accidentally passed the vector variable b or whatnot, or whatever key is close to the key he actually wanted to type on his keyboard. Or when the user has created the vectors dynamically and something went wrong there, or the user of your function read the data from a file, and maybe the file was ill formatted, and then he got corrupted data, so to say, which he put into your function, and then your function cannot cope with that. So there are lots of reasons, of course, that's just because we are humans, so we all make mistakes at some point. And the larger your software project, of course, the more errors you have in the piece of code that you write. So why does our world not crash? I mean, that's a good question that you can ask. So our world today really heavily depends on critical software systems. I mean, we have nuclear power plants which are controlled somehow using software. We have airplanes, and yeah, I guess you also wish that an airplane and the autopilot and all those computer systems work correctly before you board the airplane. Credit institutes, you also wish that if you do a transaction on the internet, maybe you have online banking or whatnot, and you are in the process or in the middle of a transaction, and I don't know, maybe one of your colleagues restarts the router and your internet connection all of a sudden breaks down. And you also wish that no money is lost in some magical ether. So you either wish to still have the money, or you successfully transferred the money, but you probably don't wish that you can lose money whenever a software system is implemented in a bad way. Cars, yeah, maybe you already have a car. You probably also wish that your car on the motorway, on the Autobahn, probably doesn't just go into an emergency stop. you wish your cars to function correctly, especially nowadays in newer car generations, which have lots and lots of automation involved, where really algorithms in software steer your car, maybe even. Also trains, for obvious reasons, right? So you don't wish to have two ICEs crash into each other because they accidentally went on the same lane. And also maybe, I mean, does your grandma use software? And the answer is, of course, yes, she does. Even if you just go to the grocery store and you pull out your credit card or debit card or whatnot, and you pay for your stuff, then I mean the cash, or even if you pay in cash, I mean the cash registers, track all the transactions and also connect over the internet to corresponding banks and whatnot. So when critical software fails, and I find that a rather good definition. So when critical software fails, people get injured or people get financially ruined, and of course we wish to avoid both. So whenever you write some critical software, which you might as well do later on in your career, be very careful, do the error handling, and do not skip the error handling. So how can you board an airplane without having fear of crashing? I mean, there's now a great example where it didn't work, which was the, what was it, Boeing 737 MAX, I guess, which had some software issues because they wanted to save a bit of money, and eventually at the very end 2 planes, if I recall correctly, crashed and many people died. So we wish to definitely avoid such accidents, really. And usually, besides Boeing 737 MAX had some technical issues, usually all such critical software systems underlie really heavy restrictions and also are standardized. So you cannot just write programs which do arbitrary stuff to control your airplane. For instance, for airplanes, it holds that you are not allowed to use any new or delete after takeoff, because it's just too dangerous. You can make mistakes too easily, so that's completely prohibited. If you implement really critical software for a car, so software that runs the engine or some emergency systems, no dynamic memory allocation is allowed at all. So you only have fixed size buffers which you can use for computations, but no new, no delete, and also no malloc and no free in the C parts of that software. So you can use error handling, of course, which we will cover today, to detect and communicate errors in your program. Also, for critical software, please use excessive testing. So write unit tests, write module tests, write integration tests. Software needs to be tested. And if you start writing tests, you will always find errors. I can assure you that from my experience. Even if you thought everything works perfectly fine, you will find some errors if you start writing unit tests, for instance. You can also try to use methods for formal verification, and you can also use static and dynamic analyses. If I recall correctly, in the last lecture I presented to you the Vagrant tool, which is a dynamic analysis tool, which you give your program basically, and then the Vagrant tool runs the program a bunch of times and stops it in between and collects data, and it finds memory issues in your program. And Vagrant is a dynamic analysis tool which can help to harden your software and to get rid of bugs. And of course, there are also static analysis tools which do not execute the software, but they're just rather looking at your software and trying to figure out some bugs and wrong behavior, essentially undesired behavior. We will have a separate lecture on static analysis, even because I mean that's what I do for my living. Yeah, already told you about the Vagrant tool, and again, our software engineering group, aka secure software engineering group, focuses on static analysis and also dynamic analysis, and I will give a dedicated lecture later on. You can also try to prove software, like in the mathematical sense, so and prove its correctness. That's usually impossible for most of the software, because many problems of that domain are usually undecidable, and so proving software is nearly impossible. Sometimes you can come up with a proof for a certain piece of your program, and that might be better than having nothing, so that can also be of interest. Some credit institutes use languages, programming languages like Haskell, which is a pure functional language, which means it makes heavily use of the type system, and it has no real state, because everything is defined in terms of recursion, or most of it is defined in terms of recursion, and so the type system will prevent you from making errors. So usually in a language such as Haskell, if your program type checks, it's usually also correct, in the sense that it can't make mistakes, because you are pretty much stateless, so to say, if you know what that means. If you don't just look up the Haskell programming language and go for functional programming languages and look up what that all means, but it's also a pretty interesting approach. And what you can also do, and most larger companies do that, if they have the money to pay those guys, get the best people for the job you need to accomplish. Bjarne Stroustrup, for instance, is currently the managing director for technology at Morgan Stanley, which is a US credit institute. So, and I guess, he will make a lot of money. I can imagine. So, okay, those are the things that you can do, and in this lecture again we are talking about error handling, so one part of this list of the previous slide. So one very famous way of handling errors and propagating errors in your program is by using return codes, and the C language, for instance, does exactly that, because the C programming language, has no exceptions, so you cannot use exceptions in C, and therefore the only possible way is using return codes, really. And because you can use return codes in C, I mean, it's a pretty generic, it's pretty simple concept. You can, of course, also do that in C++. So, and the idea is that you use a cleverly designed return code to report a problem. So, for instance, if you recall the scalar product function again, and you receive two vectors, you can check if those vectors have the same size, and if not, so then at this point the computing the scalar product wouldn't make any sense. So in this case now you can return the special floating point value, not a number, to indicate that something went wrong by and you're communicating that something went wrong by returning a special value. And then the user of your function can check for that special value and can then hopefully act accordingly. Exactly. So here we enforce basically this situation where we have two vectors of different length here, and then we're calling the scalar product function. The result will contain not a number here. And you can check for that. So there exist some functions, for instance, is nan, and you give it some value and it will tell you if it was nan, and if yes, we enter this branch here and we print something went wrong, and we can act accordingly at this point in time here. Otherwise, of course, success and result carries the desired value. We have several such special values when we are dealing with floating point numbers. So what do we have? Not a number is quite common, actually. And also you can use not a number in computations, and not a number will propagate. So whenever you specify a computation, here it's the power function, and we try to raise -1 to the power of not a number. Then if one of the operands of such a computation is not a number, then not a number propagates really throughout the whole computation, and the result will also be not a number. Yeah, and it just indicates that the value is not a number and something went wrong. But it's not very specific, right? It's just something went wrong. Better check your code, which is somewhat helpful, but yeah, for the details you have to debug your program still. We also have infinity, so positive infinity, which you can obtain if you divide by 0, which you probably don't wish to do. So you are left with infinity here. We also have a negative infinity. If you have, if you divide by 0 and then maybe put a minus in front of that to make it negative, and then you are left with negative infinity. That also holds here. So, and there is a set of functions which you can use to check for those special values. So you can use the functions which are all defined in the header C math, by the way. Is nan, is finite, is infinite, is normal, and normal would be, is none of those special values, meaning the result is correct, hopefully. And you can look up all the details here on cppreference.com. There are also other important values which you sometimes really need, and I will show you those. The numbers produced here on the slide are obtained on my 64-bit machine using the GCC compiler. There's the header file limits, which you can use to get those special values here. For instance, you can query basically some functions to give you the range. I mean, an integer type can only hold a certain range of values because it only has a finite amount of memory. Integer usually on most modern machines is 4 bytes, so you have 32 bits to store and to encode a decimal integer value. And here you can ask for the minimal number that you can fit into an integer type. So how it works is you have that special numeric limits type. This is actually a type, and then you give that type as a template parameter the type that you are interested in, for instance here in this case integer, and then you call the member function min, and it gives you the minimum number, that the minimal value that can be stored in an ordinary integer. And here, by putting the special dec or decimal symbol into the cout output stream, you tell the output stream to print whatever follows in decimal. So decimal numbers are being used here. Just to show you that you can also use some other encodings. You can also have the hex symbol here to get the resulting value, which follows in hexadecimal. So sometimes that's quite helpful, really. You can, of course, also ask for the maximum value that you can store in an integer. That would look like the following. What else could you do? You can do the same game here for unsigned. Unsigned is again a shorthand for unsigned integer, and min would probably result in a value of 0 because, I mean, you are unsigned, so the smallest value that you can store is 0, and then max is probably double than the max of a signed integer, more or less. You can also ask if you have a double data type which represents a floating point number. You can also ask for epsilon, and epsilon is the minimal value, if I recall correctly, so the minimal distance between two floating point values that can be represented, right? So Again, floating point numbers in computer science are just an approximation of mathematical real numbers, and because you only have finite memory to store values, you can basically just you have to sample on the real number line, and so there will be some numbers which can't represent it in a computer on your machine, and the epsilon gives you the distance between two adjacent values, double values. And if you compile and execute that program, it will give you all the desired values that you asked for. And yeah, here we see that for an unsigned type, the minimal value is 0, and the maximum value is pretty much double of an unsigned max value. So sometimes that might be useful when you perform some safety or security critical applications. And here you have the chance to ask for such special values. There are also lots more, so just look up what's in the limits header file on CPP reference, and we can figure out what's available. So again, let's now come back to using return codes. So return codes are a common way of reporting success or failure of a function. And the C programming language really makes heavy use of that because it has no other concept or principle that one might use. And that also means that each function that provides such a return value to indicate an error state is documented with an error code table. And then you can check for the return value and look up in the error table what that error means. Most of the time they're returning just an integer value, and then you have some documentation somewhere, and it tells you, yeah, like maybe the return value 42 means that the database connection could not be established, for instance, or could not be closed, or your internet connection could not be established, or whatnot, whatever that means for your domain. And then if you look it up in the table, you can act accordingly. So you can have some if-else, and you check, yeah, if that is 42, then I have to act and handle accordingly and do something else, probably, to make it work. Return codes are also quite common in C++ in many scenarios. That was not always the case. So I mean, in the early days, it has been taught that, yeah, just use exceptions everywhere, all over the place, but it's not all great about exceptions. So sometimes it might make more sense to use a simple return value. And return codes are even recommended in Google's internal C++ coding guidelines. What I mean, that could be completely different. Maybe if you go to Oracle or a different company, maybe they again have different internal guidelines, which then state, yeah, please use exceptions. So that's just one example here. And also the problem is that sometimes return codes are not intuitive. I mean, remember the scalar product function where you return the result as a double, and the result is the scalar product. Then you have a problem because you cannot use a return code really, because you are already returning the result. So you cannot return two values from a function. Doesn't make too much sense. I mean, maybe you can just have the scalar product function return not a number, but then again you don't know what happened really, just because you obtained not a number. Could be that those vectors have been of different length. Could also be that one of the vector's entries has been none, so you have no clue. So that's probably not very useful. And now you could come with the idea, yeah, maybe let's change the signature to have the scalar product function returning an int, and the int indicates the error state, and somewhere in your code you have as a code comment documented what, I don't know, what the return value 42 means, what minus 13 means, or whatnot. And you list all the different error states, all the different errors that the scalar product function can encounter. And the real result is returned as a reference, so as an output parameter. But I mean, that's not the purpose of functions really. So you're completely destroying actually the purpose of functions, because a function should receive some inputs, do some computations, and then return the final result. And your currently, if you would use that mechanism here, you would completely destroy it. So not very useful, I guess. So I personally, I'm not a huge fan of that. So it's not very smart, I guess. Since C++17, you can also use a smarter version to maybe indicate a failure of a function. C++17 introduced the stud optional type, which comes in quite handy. If you wish to use that, you just need to include the header optional. And it returns, yeah, you can really say that a function should return an optional type, which means it either returns a result or it doesn't. So the value that is returned is just optional, as the name suggests. So how would that look like? It would look like the following. So you have a scalar product function. It still gets two arguments, const vector int ref, x and y, and it returns as a result type an optional. And optional receives a template parameter double in this case, because we wish to return a double or nothing, so to say. So, and if both vectors are of different size, you can just return nothing essentially. So this basically calls the default constructor of optional, which indicates nothing is there. Otherwise, if those vectors have the same length, you just perform the computation and you return the final result as desired. You can also just return the result. You do not have to care. So optional is implemented in a very clever way that you can write code such as this here. And you can then do computations here, and then you can specify computations, and then you can ask the optional thing, the result has value, and if it has value, that basically means then you entered this branch. And you can also access the resulting value by calling the member function value, and it will give you the result. Maybe let's force the situation where we have two vectors of different length. So here we have a vector of length 3, 1, 2, 3, and then we give a second vector 42 and 43. So that triggers the error here. And if we now print s, the resulting value here has value, it will return false. Because, I mean, we will enter this branch in the scalar product function and return nothing, really, essentially, I mean, semantically at least, an empty optional. So that's one neat way to do it. Now let's talk about method 2. So first is error handling. Error handling by using return codes. That's, I guess, pretty obvious. Method 2 is using assertions. So you can also use assertions in your program, in your software that you're writing. How does it work? So you can find bugs using assertions, and what an assertion does, it checks if a certain condition holds, if a certain condition is evaluated to true. I mean, that's what the word assert, you assert that something is true. If that is the case, everything is fine, nothing happens. And if the conditions that you give into an assertion, if that evaluates to false, then your assertion fails, obviously, and you will receive a hard error, and your program usually just crashes or calls a termination handler. So, and that's really a hard error. So assertions should probably not be used in production code. So assertions are, the idea of assertions is that they are used while you're developing the software. And then if you are sure that your software is hardened and all the assertions always hold and everything is fine, then you can also completely remove those assertions, compile your software again without the assertions, and then ship your code to the customer. That's usually how it works, and that's usually the idea of assertions. There are dynamic assertions, which are evaluated at runtime. Why is that useful? Yeah, because, I mean, certain computations can only take place at runtime, and so the standard assertion is evaluated at runtime. and you can completely switch them on or off. So if you use an assertion in your program, it's enabled by default. But again, if you finished your software product and then you wish to ship it to the customer, you can also completely disable all the dynamic assertions, compile your program again, and then you ship your software product to the customer. And you can disable all dynamic assertions in your program by using the preprocessor flag, the preprocessor directive, or not the directive, the preprocessor symbol n-debug, so no debug. And if that symbol is available in your program, the dynamic assertions are they are completely removed from your program automatically. So you don't have to do it by hand. You start using assertions and then you just enable this preprocessor symbol here and they are automatically removed. Yeah, of course they affect runtime performance because assertions do, if you use them, they do some runtime checks, and yeah, that might impede performance somehow. How to use a dynamic assert? That's what I already told you, yeah. Here we have an example on the right-hand side. So if you wish to use assertions, dynamic assertions, you would include the header file c_assert. And here maybe, for instance, you can also pass it via the command line, but you could also have a preprocessor symbol n-debug, which you for now comment out. But if you uncomment that thing again into your program, then it will disable all your dynamic assertions. So, and you can just write some code like that here. So assert, and then you give it a condition, which is then evaluated at runtime. And if the condition fails, it will lead to a hard program crash, and then you can act accordingly. For instance, here, if you compile that piece of code and 2 plus 2 obviously is not equal to 5. So if you compile and run this code, it will crash, and it will also tell you, yeah, assert cpp 9 in int main, so in the main function in line 9. The assertion 2 plus 2 equals 5 failed, and yeah, segmentation fault has been caused here. So that's the idea. In contrast to dynamic assertions, there are also static assertions that you can use, and wherever possible, you should use static assertions instead. And the static assertions, as the name suggests, are statically, so that means they are evaluated at compile time while your compiler translates your program into a binary for most of the time. So the good thing about static assertion really is that you observe those errors even earlier, because dynamic assertions are evaluated at runtime, static assertions at compile time. So if a static assertion fails, the compiler does not even continue with compilation. It just, if it returns to false, it just immediately throws an error at you, and then you have to fix it. And I mean, that's the purpose of assertions, so that you find and fix errors. And the way it works is, there is one version, static_assert, and it's even a keyword. It receives a bool const expression, so a const expression that evaluates to a bool, to true or false. And in addition, you can give it a message, which describes the error or the problem, really. And this message must always be a string literal, so not a string literal. That's very important, because it must work statically. I mean, static assert, right? And there's also a version where you don't have a message, but yeah, to be honest, most of the time having a message is kind of helpful when someone has to debug the problem. So if possible, always provide a message. Again, if the static assertion returns or evaluates to true, if the bool const expression returns true, then the declaration here, the statement, has no effect at all. So your program works fine, or the compilation just continues and works fine. If the bool const expression evaluates to false, then a compile time error is reported. And you can And you also don't need to disable static assertions. So static assertions are always enabled because even if you have the compiled program at the very end, the static assertions already have been checked by compiling in the compilation step. So having a static assertions doesn't hurt at all. It hurts performance of the compilation process, of course, but the goal of C++ programs is to run fast, so at the cost of having longer compile times. Okay, yeah. So what I mean is it doesn't affect runtime performance, but rather it affects compile time performance because it's evaluated at compile time in a static way. So again, same game. What can we do? We can have a silly assertion here where we say, or where we wish to assert 2 + 2 = 5, and obviously again that's just false. That's not true. And if you compile it, the compiler will tell you, hey, here in function int main, error, static assertion failed, and then it will also give you the message here, this is just false, and then you can act accordingly. And the compiler will again directly abort the compilation process here, and yeah, you have to handle that error. So quite handy, quite handy. Think about the following. Errors are of course bad, you wish to avoid them at all costs, but the early error is the good error. If you can speak of a good error, at least it's better than a late error. Yeah. So the earlier you discover errors, the lower usually the costs in time and money to fix them. And also C++, of course, as C and C++ as performance-oriented languages, everything that can be done at compile time should be done at compile time, and therefore you should also, if possible, prefer static assertions. Yeah, and if you discover an error, early, it saves time, money, nerves, also very important factor, and people. If your program does not crash because you have some assertions which detected some errors, which have then be fixed, then that's perfectly fine. That's what we just desire, right? Another view on dynamic assertions. You can also think of dynamic assertions as kind of contracts, and then there's a connection between contracts and functions. Let me explain what I mean by that. So of course you remember functions, hopefully. A function gets some input, it does some useful work on the input to produce an output, and then at the very end you return that output. And another view on a function is it being a contract. So you have some preconditions that must be fulfilled before your function is applied. And if those preconditions do not hold, the application of that function rarely makes any sense. Again, if you call the scalar product function on vectors of different length, then its application makes no sense, right? So the precondition should actually be, vectors need to be of same length. And also then you might have post conditions. So a condition that must be true, that must hold after processing. And for classes and struct types, you can also have invariants, which are just some conditions that hold before and after the processing. And you can kind of enforce that and really narrow it down by using dynamic assertions. We will have an example on the next slides. Again, and if the conditions are not are violated, especially preconditions, really the application of a function doesn't make too much sense. Yeah, and those contracts can be enforced. So already told you that. Of course, I mean, some conditions are really hard to express in code, and some conditions might be even impossible to express in code. So you can also, of course, use natural language. You can use the English language because programming is mostly done in English anyways. And so you can also use code comments, of course, and that I advise you to do that if you have more complex functions. you can also write some comments for that functions and state how that function must be used, what it expects as an input and what it produces as an output. So you can also use a natural language, of course. And yeah, I advise you to comment your functions, at least the more complex ones, where you cannot immediately see and tell what it is supposed to do. And an example for the contracts and how to check them is now on the right hand side. So I don't know, maybe you need to model a car. I mean, that's a silly example, but it shows the point, and you can hopefully transfer this example to different use cases. But maybe let's say you need to model a car in code, and maybe you create a data type for that using the keyword class here. So you have a class car, and a car has a private bool, engine running, and yeah, this bool basically tells you whether the engine of car is running or not. And then you have a public interface, and you can ask if the engine is running, and the is running function just returns the bool engine running, and so it gives you the answer, does this engine run or not. And now let's talk about contracts. So if you have a function stop, and the function stop is supposed to stop the engine, maybe that's done in a different function, maybe you have a stop engine function, then it only really makes sense to stop a car's engine if that engine is running at all. Otherwise, I mean, you wouldn't really need to stop it, right? So you could assert, for instance, is the engine running as a precondition. So the application of the function stop engine only really makes sense if the engine is running. And that's here the precondition which you check with an assertion. And the post condition after you stop the engine, which you also ensure with a dynamic assert, is that the engine does not run anymore after you stopped it. And the other way around for start the engine, so before you start the engine, you should probably ask or check if the engine does not run, because otherwise it wouldn't make too much sense if you start your car again, if it's already running. And again, if you start the engine, it should probably running, the car should probably be running. So you can assert that as a post condition. So that's also one style of programming which you can use, and also which you see in practice here. A brief slide on type traits that also might be very important for you later on. So type traits have been introduced in C++11, and if you go and ask what's a type trait, if you go to CPP reference, so type traits define a compile time template-based interface to query or modify the properties of types. So type traits is really can be used to get to know about properties of types, and you can also modify them. This will become relevant later on if we do some template programming. Might be of interest to you. So if you wish to use type traits, I mean, what can you do with them? I show you some examples, and then if you wish to know more what you can do with type traits, you can go online and look it up on cppreference.com. So if you wish to use type traits, first of all, you need to include the header file type traits, and type traits are oftentimes implemented using something which is called sphere. So substitution failure is not an error. And really, it's a hell of a construct in C++. Some guys would also claim that's basically a misuse of the programming language to obtain a new feature, which is then called sphere. We will discuss what that is and how it works later on. For now, yeah, it's probably better if you not know how it works. So type properties of different categories. So you can ask about a primary type category. You can check something on composite type categories. You can check for type properties, and you can also check using type traits for supported operations. So for instance, you could ask this user-defined type, does this user-defined type have a function called foo? And yeah, you could ask that at compile time. You can also query properties using type traits of a type. And you can also check for type relationships. That becomes useful maybe later on. Once we talk about object-oriented programming, so one part of object-oriented programming is that you can form type hierarchies. And then it might make sense to check if a certain type is a parent or a child of another type. So that can also be done statically using type traits. So type traits is basically get to know about properties on types. And here on the right hand side we have a very simple example. Later on, if you need the more complicated examples, you just need to look up. I do not wish to overwhelm you with all those type trait stuff. So here just a simple example. So what you could do is you could have a struct A and a class B, and yeah, just have them empty. It doesn't matter. So still you have a type A and B. I mean, you can't do anything with them, but you have a type which is named according to the identifiers here. Bool alpha is another special value here which you can shove into the character output stream, and whenever something which you put into the character output stream next evaluates to true, it will really print the word true, and if something evaluates to false, it will really print false rather than printing 0 and 1. It will really print true or false. It's a different another special symbol. A few slides ago I told you about that decimal special thingy. Again, you can look it all up on the internet, what kind of other special symbols there are. And what you can do now is using type traits. I mean, the syntax again is C++. It's archaic. It looks quite nasty, but it gets the job done at the very end. So you can use the type trait isClass, and you give isClass a type as a template parameter. And you then have to access its value using colon. And value is not a function, it's really a value. Type traits are done by template meta programming and all that good stuff. For now, it's sufficient if you know how to use it. We will later on learn how it works and how you can do it yourself. So, and is a class? No. So this expression here, this will evaluate to false. So you can check if a type is a class or a struct or whatnot. So if you ask then is class, and then you give it the type B and access its value, so this second expression here will evaluate to true because B is a class. You can also give it some built-in types and ask is integer a class, and it will tell you false because I mean int is just a built-in type and it's not a class type. Okay, so that was it on type traits. Now let's discuss the major way of handling errors. Let's talk about exceptions, also as being the most complicated way of dealing with programming, not programming mistakes, but with programming errors, with runtime errors. And the method is exceptions here. So what is an exception here? Now it's getting interesting. So exception handling provides a way of transferring control and information from one point in the execution of a program to a handler associated with a point previously passed by the execution. In other words, exception handling transfers control up the call stack. So in even different words, that means that you can go back in time. So using exceptions are basically little time machines. So exceptions allow you to go back in time and to undo your mistakes. So that would be great to have such a thing in life. So whenever you got into a shitty situation, you can just throw an exception and then you end up 5 minutes before that shitty situation, and then you can do something else maybe. And the same principle holds here for exceptions in programming. So whenever you encounter a difficult situation, an error situation, you can, yeah, more or less just cheat and travel back in time and then do something else, do something about it, such that the error not occurs again. So yeah, it's like a little time machine. So quite interesting. And in words, so please be aware of the terminology. In computer programming, you say that an exception is thrown. So whenever you hit an error condition or whatnot, or something goes wrong, then you say that you throw an exception, like a ball or whatnot. So an exception can be thrown by a throw expression. If a dynamic cast fails, if type ID can't give you type information, then also an exception is thrown. New expressions can also throw exceptions. And some guy already observed it on, there was a question on the Panda system where some guy encountered a bad alloc exception. And that's essentially if the new keyword or the new operator couldn't do its job for whatever reasons. Yeah, allocation function, yeah, that's pretty much new and delete. And also any of the SDL functions specified to throw exceptions to signal a certain error condition. All right, so what does it mean? So an exception can be thrown to indicate an error. And also, in terms of programming terminology, an exception can also be caught. So if someone throws an exception, to go back in time, you at some point also need to catch that exception, meaning that you basically state how far you will get back in time, how far you wish to go back in time. And then if you say, yeah, okay, that's sufficient, then you catch the exception. And in order for an exception to be caught, what properties must hold? The throw expression has to be within a try block. Then you can catch an exception. Or alternatively, inside a function that is called within a try block. And the catch clause has to match the type of the exception. So, okay, that's very interesting. So that means that you can throw an exception of a certain type. So when you throw an exception, this exception has a certain type. And then you can catch this exception if it occurs in a try block. We will learn on try blocks in a few seconds. And apparently you can catch the exception if the exception that you wish to catch matches the exception that is thrown. Okay, so far so good. Yeah, already told you all that. And the control flow is basically transfer to an earlier point in the program where the error can still be handled. And also on the on some, I guess on 2 slides, I will also tell you about some places where it's really not wise to throw an exception. So there are some places where you are essentially not allowed to throw an exception. And that's very important, and you need to be aware of that. Why is that? I mean, that's just necessary to guarantee resource safety, which is a very important property. So let's have a simple example. And again, that's a very naive example. I mean, that code doesn't do anything useful, but you can hopefully transfer this situation into a more exciting situation, maybe. So what do? We initialize ourselves a vector variable v containing the elements 11, 12, 13. And you see the valid indices of v would be 0 to 2. 0th element, first element, second element. And then we define a very stupid function which is called get, and get receives a vector variable and an index, and it will just give you a double reference to the value at index or position 0. So the value would actually be a double reference to that 11 value here stored in the vector. And of course we can also print it. And you probably also already noticed here what can go wrong if you just use get blindly and if you do not really care about size. So let's define the get function here. The problem here is if the index, namely, is larger or equal than the vector's size, then we are in trouble, because I mean we are out of bounds. If a user calls the get function and the index is greater or equal than vector size, yeah, we are out of bounds, and then that would be undefined behavior. So here we are in huge trouble. So what can we do? What we now can do is we can throw an out of range exception. So here we throw an exception, and the exception type is out of range. So out of range is a certain exception type, which is specified here in std_except. Std_except is just a header file which you need to include if you wish to use exceptions. And this basically tells, oh, this is a nasty situation. I wish to go back in time. Can I go back in time, please? And then, yeah, you go back in time. So you got away with it. Otherwise, if that's not the case, then everything is perfectly fine, and we can now return the vector at position index. Yeah, that's the good case where nothing bad happens here. So, and now I've thrown an exception. So what else do I need to do? What else do I need to know? I already told you that you need to catch the exception at some point. And how that works is you need a try block. So you can use the keyword try, then you give it a body, so to say, a compound statement. And this introduces a try block. And here you can now force or trigger this bug here, the index too large condition. And maybe you can call your get function with a v and the index 100. And now this triggers the exception to be thrown. And the exception now goes back to the catch. And at this point, you can catch the exception that has been thrown here. Because here at this position you try to catch, so you wish to catch an out of range exception. So and here within that function you have exactly thrown an out of range exception. So you would catch this exception, and in this error condition your control flow would be transferred to the catch block. So each try also has a catch. And whenever an exception is thrown within the try block, it's hopefully caught by the corresponding catch block, where you can now do something else. And here you are essentially within the catch block, you are back in time, because you transfer the control flow from here to here. All right. And also one thing of importance is that a catch block, so everything that is in parentheses after catch, is also called exception handler, because it handles an exception and it deals with the error. And you can also transfer some messages here. So you can give out of range, this out of range exception, you can also give it some string message, which you can then with the member function what, which you can then access. And for instance, print to the command line, and then you can see what went wrong. So what is an exception exactly? An exception is a type. An exception is a class that contains all information necessary to perform the job that needs to be performed. The std_except header defines the following useful exception types. So you can throw in logic error, invalid argument error, domain error, length error, out of range error, runtime error, range error, overflow error, underflow error. And you can also define your own exceptions. That's also possible. So how you would do it is you would inherit from an existing exception class, and then you can adjust it to your needs. Maybe we will talk about that later on, how you do it. Otherwise, I mean, I never really defined my own exception. I instead always used one of the standard ones. But you can do it. You can define your own things as well. might be useful if you need to implement a larger library or whatnot. Well, a very domain specific thing. Yeah, depends on your purposes. Really. Please don't do the following. So what you can also, of course, do is you can have you can basically put a try around your whole main. So meaning that your whole program is actually executed in a try block. And then whenever something is wrong, you collect all the runtime errors here, and then you catch them, and yeah, oops, something went wrong. Okay, so I mean, please don't put your whole program as is in a try block. That doesn't make too much sense. But I mean, it would be possible, and you see how one would do it. Yeah. So do or do not. There's no try. I mean, sometimes there's a try, but not in that scope here. So how about the scalar product? So what handling would be adequate? Return codes, assertion, exceptions. So it's a really tough one to answer. It really depends on a lot of things, which I can't tell you. Depends on your domain, on your purpose, on your application scenario. So really you have to make the decision. Here in our simple case, yeah, we could probably use exceptions, and we could throw in logic error if those two vectors are of different dimensions here. Otherwise, you just continue with your ordinary computation if here everything is fine, and you return the result. And then you have some user-generated data, and here maybe let's enforce this error here by providing two vectors of different length. We can now have a try block, and it has the scalar product, which may throw in a try block. Then we can associate as a corresponding exception handler here, which catches logic errors, and here you observe that the types match. So whenever we throw an exception, logic error exception, we also need to catch a logic error exception. And then we can here act accordingly, and yeah, whatever that means, it depends on your domain. Maybe if you read some user input and you catch an exception because the user input has been rubbish, maybe you can ask the user again, hey user, here your data has been invalid, please try again, and yeah, give me some sane inputs. It depends, so you can maybe repeat the thing you wish to do and ask for new data or whatnot. It really depends on your domain and your problem. What else? So never catch like this here. So throw on logic error here, and then just have a try where you try to call your scalar product and have an empty catch. So you can really see this in practice. So this is just ignore whatever exceptional error just happened, just ignore it and continue as nothing has happened. This can be especially seen in the Java world quite often. So yeah, this can be really seen in real world code, but please never just ignore exceptions. So an exception is again an exceptional error, and you have to do something about it. Don't just ignore it. And what's also possible, you are also allowed to rethrow. What does it mean? So that means that you can execute your scalar product function, and maybe here you trigger the throw, and then it throws an exception. And then you end up in the corresponding exception handler, in the first exception handler that matches the exceptions type, which would be this one, because here logic error that matches here. So then you can do some stuff, you can execute some code, but then you can also say, yeah, throw again. And then that basically means, yeah, rethrow, throw the exception even further up the call stack, and then you would try to find the next exception handler, which also catches a logic error. So you would now go even further upwards, you would go even further back in time when you rethrow. So that's also possible. there might be some use out there, but I never used it really to rethrow. Either I handled it correctly or I didn't, but yeah, maybe you find some application for that at some point. And I already told you that if an exception is thrown, the stack is unwound for you. So there exists something which is called stack unwinding. And that is really the great benefit of exceptions. So if you use exceptions, you have built a mechanism which is called stack unwinding. And that's really a good thing, which we will discuss about right now. I give you a high-level overview, and then for all the details, you just need to refer to some web pages or books or whatnot. So, I mean, there are books and papers on this topic, so I can't give you all the full details, but I try to give you a rough understanding of what stack unwinding is. Otherwise, I mean, you can look up all the details in CPP reference and search your way from there. So the principle is not very complicated at all. So maybe let's just go with an example again to give you some kind of clue. So maybe let's develop our own vector type or our own data type, which we here just call just A, which manages an array of dynamically allocated memory. I mean, similar to your homework. So we give it a constructor, it receives the size, and it has a pointer to an integer as a member. And here it dynamically allocates an array of size integers, and it puts the pointer, it stores the pointer in that data member mem for memory. And in the destructor, it array deletes whatever mem points to, so to get rid of the dynamically allocated integer values, right? So far, so good. I hope that's pretty much clear by now. And now the following happens. Let's have a small example. So what happens now is, what you can do, how stack unwinding works is, you can now have a try block where you, for instance, have two variables of type A and B, and this variable A, when calling its constructor, allocates a dynamic array on the heap of size 2, so for 2 integers, and B also allocates, of course, in its constructor an array on the heap of size 4, so space for 4 integers. So you are doing some stuff, right? So you're initializing memory, you're allocating memory, you initialize it, and then you maybe perform some computations, you have some more code which follows. But maybe at some point you might hit a throw, and here I just wrote a plain throw in order to prove my point. You would probably not do that practice here, at least without checking a condition or so. So here now I throw a runtime error. And I pass the message crash here. And now what the runtime error does here, which is thrown, it transfers control flow to the corresponding matching exception handler, which would be this catch here, because this catch also catches a runtime error and we throw a runtime error. So type system checks out, and here we catch hit and print gotcha to the command line, to the character output stream. And now what stack unwinding is, before we not just go to the exception handler immediately when we hit a throw. No, what we do before we go back in time is we unwind the stack. That means whatever has been done before here in the code before the throw is, you undo it basically. So you unwind the stack. So for instance, if you hit throw here, you then go back in time through the stack here. You go up the stack, and here you see, I have now there is. We have been at this point, and so B has already been initialized, and its constructor has been called. So and now if we throw an exception, we essentially go back in time and unwind all the stuff. So that means here, oh, we constructed a b, so probably we wish to deconstruct it. So, and then for the variable b, its deconstructor is automatically called. So, and the destructor deletes the dynamically allocated memory. And then we got rid of b, so we got b off the stack, we unwound it and called its destructor. So we undid the thing. And then we see, variable a also exists on the stack. No, I should probably also call the destructor for that. And then also a's destructor is called, and it's freed. And yeah, so we have gotten rid of everything that's here on the stack before we hit the throw. And then we are transferring control flow to the exception handler, which is specified right here. Okay, so and the good thing about stack unwinding, it does the cleanup for you. So if you encounter an error state in your try block, then everything that has been done before within the try block is automatically undone for you, which is great. So you don't have to clean up, and no leaks are possible because all the matching destructors are called. So it guarantees resource safety, which is pretty much what you want. You have some problems with unwinding the stack. Stack unwinding might also fail, and we will have an example on the next few slides somewhere, where I show you some example where exception handling fails or can fail. When exception handling fails and the stack cannot be unwound, then terminate is called. Terminate is a special function. Terminate is called whenever an exception is not caught, when another exception is thrown while exception handling. So very important to notice in C++. In C++, you can only have one outstanding exception that is then handled. Whenever you already have one outstanding exception which is currently handled, and then you throw yet another exception, then your program also is directly terminated because you can't have that. That's not allowed in C++. And there are some more cases. And what does terminate do? Terminate calls a terminate handler. So that's a special function which is called, which does some maybe last things before the program eventually dies. This might be particularly interesting to fight against data losses. So maybe your program encounters an exception, and then something goes wrong in the exception handler itself. Yeah, might happen. And in the terminate handler, you can maybe save data. Maybe you have some unwritten data. You can then in this function write all the data. I don't know, if you have some Word documents with very important stuff, it would probably, before your program eventually dies, it would probably be good to save that data somewhere, and to make a last effort to save as much as possible, whatever that means in your use case, in your domain. The terminate handler then usually leads to hard program termination. But you can also install your own terminate handler with the set terminate function. Again, on the last few slides today, we will talk about function pointers, and that's one use of function pointers here. You can define your own function, your own terminate handler, which you just call my handler or whatever. I mean, you can choose the function name as you wish. And then maybe you just print my own termination handler, and then you call abort, which then completely kills off the program. And then you set the terminate handler, and you give it as a parameter the custom handler. So your own handler is installed. And then you throw an exception. You can then just throw, and you never catch it, and then your termination handler is called before your program is killed. And you can write such piece of program and compile it and run it, and you will see that my own termination handler will be printed, and that the system works here. So when we are talking about exceptions, it's probably also interesting that you can specify functions as no-except. No-except is a keyword. And functions can be specified to be no-except, to be guaranteed not to throw an exception. For instance, that might be useful for small and simple functions that really cannot throw an exception. Yeah, again, a made-up example, very simple. If you just have to do some arithmetic here, two ints, and you add them up together. And I mean, this piece of code obviously does not throw an exception because, yeah, I mean, you see there's no throw in it. And then you can also add the keyword no-except and annotate the function with no-except. First of all, the keyword is about semantics, so you can immediately see that this function does not throw an exception, which is might be a good thing. I mean, it's of similar use in specifying member functions to be const. If the member function does not modify its data members, then again, it also makes sense to specify it as a const member function to indicate to users that this function does not modify its members, of course. It may also lead to a performance increase. So compilers may generate faster code if they have a no-except function. So that might also be the case. But please don't use it blindly, and please do not just annotate each function with no-except, because even if your code doesn't throw an exception, if you implement a function which then in turn calls a different function which throws, then your function throws as well, because it's about transitivity. So if you implement a function which calls another function which eventually throws, then your function is not no-except anymore. So be careful. And also, please do not lie to your compiler. So what happens if you lie to your compiler and if you throw an exception which is actually marked as no-except, then terminate will be called, which causes program termination at the end. And in general, it's not wise to try to trick the compiler. You can also specify functions as throw. That's also possible. So functions can be specified to indicate that they may throw. I quickly go over that because it's not really relevant anymore. So you could annotate your function with a throw, and then you give it the types that might be thrown. However, I advise you not to use that at all. Here it was also about semantics, blah, 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 but it doesn't really matter. So it's not good practice. So please don't use the throw annotation, because the trouble really is that the compiler cannot check if really only an out of range is thrown or something else. If you throw something else here, the compiler cannot check that this what can be thrown, or at least what's annotated what can be thrown, matches what can actually be thrown. That cannot be compiler checked. And therefore it doesn't make too much, or it doesn't make any sense really to use it. So the annotation with throw was just a bad idea. So if you see it on the internet, please don't do that. Another point here, why should I care at all about all these specifiers and qualifiers? Why should I declare member functions const? Why should I declare any function no-except, whatnot? So reading code is not always easy. You probably already figured that for yourself. And if you use speci and qualifiers, that might help to improve readability, first of all. So good code should always document itself. So if you read some code, you should more or less immediately know what it does. If that's not the case, you should maybe think of rewriting your code such that you know what it does just by looking at it. So that also includes finding useful names for variables, functions, structs, classes, all the good stuff. So find useful names for identifiers. And I mean, also the great thing about header files, if you read a function declaration, you should immediately have a good idea, a rough idea what that function does. So you should be, just by looking at the function declaration, know what it does, know how it has to be used, and also know how it behaves. but not necessarily how it does its job. Because yeah, that really depends on the implementation. If that's not the case, then you should rewrite your code. To give you some examples, I mean, the function matrix multiply. Yeah, it hopefully will do. It will perform a matrix multiplication on the two matrices specified as const ref A and B, and the result will also be it will return a new matrix, which is the result of this matrix multiplication. So, and here just by having the declaration, the function declaration, you can immediately tell what's its job and how it should be used. Also, if you just have a simple function add, I mean, you know what add should probably do. I mean, add up A and B. It's also no except, so meaning that it doesn't throw an exception, and the result is also an integer, namely the sum of A and B. And vec3, yeah, represents three doubles here, vectors of vector space R3. You have constructor, you have Euclidean length, which gives you the Euclidean length of that vector. I mean the mathematical length. And yeah, those are some examples. So let's talk about pros and cons of exceptions. So pros, what you do is, if you use exceptions, you separate your error handling code from your normal program flow, which is probably a good thing, because then your normal flow you can implement as usual, and if you hit an error, you can just throw an exception and then the error handling code is somewhere else, so you don't mix it all up, which is the case if you use return codes. Also, throwing exceptions is the only clean way to report an error in constructors, because constructors have no return value, which you could check. Of course, you could use an output parameter, some reference or something like that. Wow, it's really ugly. So, I mean, the only clean way really is to throw an exception in constructor. Exceptions are also hard to ignore, so which is a good thing. So you as a programmer are forced to deal with that error, otherwise your program will just crash. So hard error, it can't be ignored really. It's also easy to propagate errors from deeply nested functions because of the automatic stack unwinding that is done for you. And it carries also much more information than an simple error code. Maybe you use an integer for an error code there, then you have to document yourself and all that stuff. And using exceptions, you can transfer and propagate more information about the error. Also, exception objects are matched to the handlers by using the type system. So each throw has a corresponding catch, and if the types match, then the handler is used to handle that error. And again, yeah, automatic stack unwinding, which is very important, very powerful. So on the negative side, you break code structure by creating invisible exit points that make code hard to read. So if you have some nested functions and then maybe one function might throw, yeah, it's really hard because you cannot see the control flow paths really, right? I mean, you know what's going on, but you can't see them directly in code. It's only implicitly encoded, so to say. So if you use it wrong, you can introduce resource leaks easily, of course. That's also not a good thing. So it's also pretty hard to write exception safe code, but it's doable at least. Might be expensive. Compiler optimizations sometimes do not like exceptions very much because it's harder for the compiler's optimizer to see through your code. So might be harder to optimize for the compiler. And also it breaks the paradigm, only pay for what you use. I mean, even if you have exceptions and you never throw, it might still be a performance penalty, because the optimizer just can't understand the code the way it could understand it when you don't use exceptions. And when the compiler is confused, or when the compiler's optimizer is confused, it won't do anything. hard to introduce to legacy code. Yeah, if you have an existing huge code base that has no exceptions, it's very difficult to impossible to pull it over after you already have a software project which doesn't use them. It can also easily be abused for programming tasks that do belong to normal program flow. Yeah, I don't wish to nag about Java all the time, but I mean, I really saw some nightmares implemented in Java. There's a compiler project in Java. And in that compiler project, I don't tell you the name for obvious reasons, because otherwise here Mr. Philipp Schubert told that this project is rubbish. I mean, it isn't rubbish, but what they do in that project is they use exceptions and the exceptional control flow to encode really desired behavior. So, and that's really the least thing that you should use exceptions for. So I don't really understand why they do it, but apparently, yeah, it works for them. Again, it can be abused. You probably shouldn't do it. So when to use what as a rule of thumb? So it's difficult, first of all, but I found the following good post on Stack Overflow which discussed when to use what. So use assertions to catch your own errors, the errors you are responsible for. So use assertions for functions and data that are internal to your system, where you are in chief and responsible for. Then you should use assertions to catch those errors. Use exceptions to catch other people's errors. Probably also makes sense. So rep calls to public APIs in exceptions maybe. If you have an API that receives user data and you cannot be sure what the user provides, you probably wish to wrap that in a try block and make use of exceptions. API is, by the way, an application programming interface. So basically all the public member functions, that would be called an API, for instance. And also, yeah, as I said, when dealing with a data that is external and not under your control, then exceptions are probably the way to go. And yeah, return codes are the performance exceptions. So yeah, that would be it from my side. The rest is up to you. I promised that I told you about at least 2 places where you should not throw an exception. So, and what you have to keep in mind is this sentence here. So you cannot throw in destructors and you should not throw in constructors. Because if you would do, nevertheless, I mean, you can of course do that, but you have huge trouble. So let's first talk about you cannot throw in destructors. So think of a dynamically allocated array of variables of a user-defined type. So as a type as you implemented in your homework, or I showed you in the stack unwinding example. So a type which does some dynamic memory management. So it allocates stuff and it deallocates stuff in its destructor and all the good stuff. So and then think of an array. Say you have an array of those objects which do the dynamic memory handling, and then maybe you call delete because at some point you wish to get rid of all those objects. So what happens if an exception is thrown while destructing the second argument? Yeah, maybe that happens. So maybe you have an array of objects and you call all their destructors and then exception is thrown. So what do? Abort could be, but then you leak. Then you leak the remaining third to whatnot to nth element. So you leak memory, or sometimes even you leak connections or whatever your types implement. What else can you do? You can ignore and continue destructing the remaining variables. But if you just ignore the exception, you have one outstanding exception that you just are about to ignore. But C++ can only have one outstanding exception. If then the destruction of a different object that comes after that fails again, you have 2 outstanding exceptions. And yeah, you leak and terminate will be called. And your program just crashes, so which is not what you wish to do. So the question really is, do you feel lucky? So probably it's not a good idea to throw in a destructor, so you probably shouldn't do that. And you also should not throw in constructors, although it's the only clean way to report an error. But what happens if an exception is thrown within the constructor? The problem then is really you fail halfway through. So maybe you already initialized and allocated a bunch of stuff, but then you fail, and then you are left with an object that is constructed halfway. So you then the stack unwinding doesn't work anymore, because you have a half constructed object, and then you really need to deconstruct and undo everything yourself, which is terrible. So destructor cannot be called because it's not completely constructed. No stack unrunning can be performed. You have to do it all yourself. Also, using a return code is not really possible in constructors. So that's the other problem here. Yeah. So that would be pretty much it on error handling. So return codes, assertions, exceptions, that are the main ways of handling errors in your program. Now, on the last few slides, let's go to pointers. Let's have a look at pointers one more time. So pointers again, yes. Remember pointers. So pointer is, yeah, you can have an ordinary integer value, a variable I, and you initialize it with the value 42. And then you can have a pointer to an integer in star IPTR, and then you let it point to the address of I. So you let it point to I. And please observe that the ampersand again is the get address of operator. So far we only really have seen pointers to variables, but there's also something more bizarre thing possible. Because, I mean, think of functions. I mean, functions are also in somewhere in your code, because, I mean, you need to execute them. So functions and the code associated with those functions are encoded in your program. And so functions also have addresses. And, I mean, that's of course clear that you then can also have pointers to the address of a function. Function pointers, yeah, pointers to functions. So how does it look like? Again, the syntax is brutal, but what can you do? So this is a function pointer declaration here, or definition even. So f is a variable. F is a variable of type function pointer. So you can give your variable an arbitrary name, like f here in this example. Then you put a star and parentheses around it to make it really a function pointer. Here you have the return type of that function. Function pointer. And here you have the parameter list of that function pointer. And at the beginning you initialize it to the null pointer. So f is a function pointer which is initialized with the null pointer. So f is now a variable of type function pointer to a function of type receiving two integer arguments, returning an integer argument. So in words, f can point to every function that matches this signature. Meaning f can point to any function that gets two integer parameters and returns one integer. That's the semantics of the function pointer. That is what the syntax here means. So a concrete example. So let's have a function multiply. So it gets two integer arguments, and it just returns the multiplication, the product of those two integers. And then you can, for instance, have another function which also receives as a parameter a function pointer. So you can also have function pointers as parameters. So you now have a different function which is called perform binary operation, which receives two integer arguments a and b. And as a third parameter, you receive a function pointer which can point to functions which receive two integers as arguments and return one integer. And then your perform binary operation, you can use that function. You can, for instance, just apply and call that function and apply it to A and B, and whatever the result is, you return it as your own result, so to say. And here's an example how it would work. So you can now call the perform binary operation with two integer arguments, 4 and 5. And here you give it the address of the function multiplication. So and you use here the ampersand here to say, yeah, this function pointer should be multiplication function. And then the result would be 20, because perform binary operation calls whatever function here is provided and applies it to the arguments A and B. So why is that useful? Why would you ever need such a thing? The great thing is now that you can pass functions as parameters, as you saw on the last slide. And maybe please recall the integrator program, integrator.cpp, which we had in one of the earlier exercise classes. So you can now improve on your integrate function, and you can not only give it an interval specified with from and to and the number of sampling points it should use for integration, but you can now also abstract away the concrete function that should be evaluated, and you can just make the function to be evaluated a function pointer, and therefore you make it a parameter in this case. So your integrate function receives as a fourth parameter function pointer with the following signature, receiving as input parameter 1 long double and returning as a result 1 long double. And then you have your ordinary integration code. And here at this point you just call to the function pointer. You call the function pointer. And yeah, congratulations, you have now abstracted away a concrete function. So you can now integrate every function that matches here this function pointer signature, really. Okay. And because dealing with function pointers might be a bit fiddly and nasty and whatnot, there's also a wrapper type provided in the STL. So within the standard template library, you have the stud function wrapper. Which you can use instead of fiddling with raw function pointers. So how you would do it is basically you use this syntax here. So you use the type, the stud function type, and the stud function type receives as a parameter a type. It's a template parameter here. Again, we will talk about templates and template metaprogramming later on. And the type that your function receives is basically, returning one integer and receiving two integers as arguments. And you name that function f, as the function parameter here. And then within the function, you just apply f, whatever f is, to A and B. And then you can call your perform binary operation here, give it the integer literals 2 and 6, and give it as a parameter the add function here. So it should apply in this perform binary operation, it will apply add to A and B, and the result would be 8 at the very end. And also notice that here at this point you don't have to use the ampersand. So whenever something desires or whenever something expects a function pointer as an argument, you don't have to use the ampersand. You can use it to be correct, but it would also be correct to not to do the ampersand, because it wouldn't make any sense to, a function which you pass as a function pointer parameter, it wouldn't make any sense to dereference that thing also. So then the compiler is smart enough to see what you mean here. You mean that you pass the add function as a function pointer here to the other function. So you can do the ampersand, but it also doesn't matter if you don't do it for the compiler. It's the same thing, because everything else wouldn't make any sense, which is why both things are allowed. So in that would be pretty much it for today's lecture. So a recap, why we talked about why error handling is important. We talked about the different ways of handling errors, return codes, assertions, exceptions. We talked about special floating point values, and also I presented some functions and templates and type traits and whatnot, which you can use to check types, error conditions, and such things. And also we briefly discussed on when to use what kind of error handling, but ultimately it's a decision that you have to make on your own, depending on the problems that you're working on, and also depending on the domain and whatnot. So it's difficult to tell, but there are some rule of thumb. There's some rule of thumb, really. And then at the very end, we had a brief look on function pointers and also on a wrapper type for function pointers in the STL, which can also do a bit more, which is called std function. The type is called std stud function. So you can look it up on CPP reference and see what it can do, what it can do in detail. All right, then thank you very much. That would be it for today. So see you this afternoon in the live stream, and otherwise have a long and extended weekend. So be aware that Monday is a national holiday, which I myself also forgot again. So a colleague had to remind me on Wednesday that Monday is a holiday, but whatnot. So yeah, please enjoy your long weekend.